I'm Craig the geologist, and there's a lot of information about rocks out there. But one thing we don't hear about much are rocks' thermal properties. Can we learn anything about these rocks by having a look at the way they behave when they're heated up and when they cool? Can we learn anything new about them by looking at them in a different way, say with a thermal sensor? Well, let's find out. Come join me. Hi, I've brought you to the only clean corner of my house to show you these three beautiful pudding stones. Why pudding stones? Well, there's nothing thermally unique about a pudding stone, but for the demonstrations we're doing today, I wanted three identical rocks of different sizes. Now, visually you can see that they're not truly identical, but they are all Lorraine formation metaconglomerates. They're all pudding stones. And so for what we're doing today, that's good enough. So the first thing I want to talk to you about is heat capacity. What is heat capacity? Well, it's a measure of how much heat a material can hold. That's different from temperature, although it doesn't always feel intuitive to us. You can think of it this way. If a temperature is a measure of how hot a material is, heat capacity is a measure of how much heat that material can lose before the temperature starts to change, or vice versa, how much it can gain before the temperature starts to change. Water has a very high heat capacity. It has one of the highest heat capacities of any substance on our planet. And so it's used in coolant systems all around the world. Think about holding an ice cube in your hand versus holding maybe a marble of the same size or a piece of wood of the same size. You will change the temperature of those other materials far faster than you will change the temperature of that ice cube. Your hand's going to get real cold before that ice cube melts. Materials with a low heat capacity can be very handy as well. Take, for example, aluminum cookware. You throw your pot or pan on the stove, turn up the heat, it's hot within a matter of seconds and you're already cooking. If you want to cook your food a little bit more evenly, maybe cook with cast iron, which has a little bit of a higher heat capacity and will let go of its heat a little more slowly. Water, of course, you turn the kettle on, you boil your water, you pour yourself a nice hot cup of cocoa or tea or coffee, it's going to stay hot for a very long time. All right, on the right, I've got a kettle full of water that I've heated to boiling, and on the left, I've got a room temperature pan, which appears mostly invisible in infrared because it's the same color as everything else. Let's change that. All right, I've got a gas stove. It's heating up that pan very quickly because it has a low heat capacity. Also has a high thermal conductivity. We'll talk about that in a minute. But it doesn't have a lot of heat storage capacity in the material itself. So it gets hot very quickly, and it will also, as I think we'll see in a moment, cool down very quickly as well. At the top of the screen, you will see a scale bar for temperature. It's a dynamic scale bar. It's constantly changing so that the hottest thing on the screen is a bright yellow and the coldest is blue. Now let's put these two objects next to each other and see the temperature change. We don't have the patience to watch this for 2 straight minutes. It's pretty dull. So I've sped it up by 10 times. After about a minute, we can see that the temperature of the water in the kettle hasn't changed at all, while the temperature of the pan has dropped from about 100 degrees Celsius down to around 50. And in fact, the aluminum part at the bottom that has the fastest heat exchange has already dropped to room temperature. I can actually touch it and it is cool to the touch. So in summary, while the pan and the kettle full of water reach the same temperature, the kettle of water holds a lot more heat than the pan does. It has a much greater heat capacity than the aluminum pan. The other property I want to talk to you about in terms of these rocks is thermal conductivity. Now that's a little bit of a scarier scientific sounding name, but actually it's very simple. It's how easily a material transfers heat from one object to the next. Now, let's talk about going into a sauna. You walk into a sauna and it's 160 degrees in there. Someone's got it piping hot. But you're not getting burned by that air. The air has a very low thermal conductivity. It doesn't transfer the heat to you very efficiently. And so you're okay walking in. It just feels toasty. And then you sit on that wooden bench that's also 160 degrees. That feels hot. That has a higher thermal conductivity. It burns your lungs a bit. But you get settled in, you're okay. And then you reach over and you accidentally touch something that's metal. Metal has a very high thermal conductivity. That metal is the exact same temperature as the air and the bench you're sitting on, but it burns you because it transfers that heat very quickly. Let's go to the beach and have a look at this.
Here I am, proving that I look amazing in every single wavelength of the electromagnetic spectrum. I'm at the beach at Lake Huron, walking across a pretty hot boardwalk in June on an incredibly hot summer day. It was unseasonably hot this day, I believe between 90 and 95 degrees. So that sand is toasty, the boardwalk is toasty. The water, however, is still extremely cold, not fun to swim in. It is frigid out there, and that's why it's blue. Now I'm gonna make my way out to probably the oldest slide I've ever actually seen in any park anywhere. I've talked to an old timer who told me that this slide has been up since the 1940s at least. It is a metal slide. Nice, big, tall, old-fashioned, pure metal, designed to burn children. And so I figure that's the perfect place for a demonstration of these heat properties. And here you're seeing the temperature patterns on the sand. I'll talk about those in a little bit, but that's kind of interesting too. Now here I've discovered something unique that I probably should have been able to predict, but didn't. And that's that the slide is reflective in infrared. Now, I mean, it's a pure sheet metal slide. It's extremely reflective to natural light. I assumed that I could read a temperature off of the reflective portion, but it turns out it just reflects the sky in infrared. So here I am using the sides, and it is burning the heck out of my hand. You can see it's registering at about 50 degrees Celsius. That is pretty warm. That's 122 degrees Fahrenheit, and it is not comfortable because, as mentioned, the high rate of heat transfer, that thermal conductivity, really puts all that heat straight into your skin fast. Here I'm going to burn myself for science. Here's my nice cold hand. There it is on the side. I'm trying to cool the slide with my hand. But notice I'm doing a pretty terrible job, although I am doing a great job of burning my hand. That's thermal conductivity in action. All the heat in that metal slide is moving to achieve an equilibrium. Any heat goes out at one point, heat from the other parts floods in, and overall the temperature of the slide does not change much. Now I'm looking at the sand. I found this real interesting and kind of beautiful. But the surface of the sand, extremely hot. But you kick the surface away and you reveal the cool sand underneath. And that can be a trick if you're burning your feet walking across the sand. Kick sand as you go and try to step in the cooler parts. I was burning the heck out of my feet when I took my flip-flops off. It can be torture for anyone who's been to the beach on a hot day. But the sand just an inch below the surface, much, much cooler, much more comfortable to walk on. Honestly, I think there could be a market out there for thermal artists. I thought some of the designs were pretty interesting out there. Now I've moved back to the boardwalk with the aim of illustrating thermal conductivity again. Remember, when I placed my cool hand onto the metal, there is no temperature change because the metal transferred the heat so quickly. On this, though, there is a temperature change because the wood does not equilibrate quickly. It doesn't transfer the heat from the edges of the wood to the center where my foot has cooled it down. And so that's kind of what I was talking about with the bench in a sauna. You know, when you sit on it, it's initially very hot. It burns your butt cheeks, but after a few seconds, it's cool, you're comfortable, because you don't have all of the wood transferring all of its heat into you at once. Here I'm sacrificing my feet for science, burning the heck out of my feet, and showing that, okay, we have a higher thermal conductivity for the sand, higher than for the wood, but lower than for the metal.
So different materials have different thermal conductivities. Take, for example, the thermal tiles on the space shuttle. They do not want the inside of the space shuttle reaching the thousands of degrees of re-entry. And so they've got thermal tiles on there with terrible thermal conductivity. In fact, you can pick up those tiles while they're glowing hot still because they transfer the heat so poorly to other objects, including your skin. That's not the case for metal, which is famously good for conducting heat. It's good for cookware, not good for burning yourself on a hot slide. Rocks also tend to have a very high thermal conductivity. They transfer the heat very quickly.
Thermal conductivity demonstration, my rocks versus my old Michigan Tech Geology Department sweatshirt. Now, a sweatshirt is going to have very poor thermal conductivity. That ought to make sense to you. It's a terrible sweatshirt that transfers all your heat away. We're going to begin with the sweatshirt and the rocks all at about the same temperature. But let's put a handprint on them and see what happens. I'll leave my hands on there for a few seconds. Let my hands warm up the surface of each of those and we'll see just what happens. I pull my hands away and the heat from my hands remains on the surface of both objects. But it's not the same, is it? The sweatshirt with this very poor thermal conductivity retains the heat from my palm, whereas the rock with the very high thermal conductivity has transferred the heat from the surface of the rock down into its interior with its high heat capacity, and you cannot see the thermal signature from my handprint any longer. In fact, just in case you thought it was a fluke, maybe I was using a cold hand, or maybe it's the angle, I've done it again, and once again you can see the heat transfer from the surface of the rock into the interior. All right, let's take these rocks outside. All right, well, I'll tell you, this rock is a heavy beast. And I think I'm going to place it right up here if it can hold it up here. There we go. All right, so we're gonna leave this set up here for a few hours, maybe even a few days, depends how long it takes to change temperature. I've got this big guy set up here. I've got two smaller ones set up on a porch over here. Now, this isn't great for rocks. What happens is the change in temperature puts a lot of stress on a rock, so I wouldn't do this very often. But what you end up with in many cases is the rock expanding as it gets warm, contracting as it gets cold. We'll talk a little bit more about that later, but it can end up cracking and destroying your rocks. So you don't want to do this too often. You know what? I do want to talk about spalling for a moment, so let me just interject. Look at this awesome picture of me, so young, so vivacious, 15 years ago at Girraween National Park in Australia. These granite boulders are exhibiting spalling right here. During the day, the boulders get incredibly hot. At night, the temperature drops and they cool back down, and that constant thermal expansion and contraction causes layers to separate, crack, and fall away, and that's called spalling. It's common in rocks all around the world, especially in granites. This is a granite slope at Yosemite National Park, and you'll notice that there are large flat slabs breaking away along the slope, and that is an example of spalling too. Spalling is very common on exposed mountain faces. If you're having trouble spotting the spalling in this photo, it's happening in these places here. All right, let's get back to our experiment. So we're starting this experiment at 10:30 in the morning, and I've got my small stones on my porch right here. I've got the larger pudding stone on a pedestal of a tree stump I've got next to my driveway. What you're noticing about this, I would expect, would be the speckled pattern on it. That has nothing to do with the composition of the rock with the stones that are in it, but it's actually what you're seeing are the pits in the rock, where the interior of the rock, which is warmer, is shining through brighter with that higher temperature. An hour later, and that large pudding stone has dropped in temperature quite a lot, but is still significantly warmer than its surroundings, especially compared to the snow behind it. Interestingly, that tree stump is in the sun, and it's warming up really fast. Meanwhile, on my porch, and you can see the black colored snow shovel in the background is catching that sunlight, but the medium and small pudding stones are still holding on to their heat, although the medium-sized pudding stone significantly warmer now than the smallest pudding stone. So we are seeing that small one lose its heat faster than the larger ones. All right, now it's 1:30, we're 3 hours in, and we're seeing more of the same. The large pudding stone is still cooling, but it's still significantly warmer than the snow around it. And when we go to the smaller pudding stones, we're going to see that those are also dropping in temperature, but they're still warmer than their surroundings. All right, 5:30 now, we're 7 hours in. The rock is cooling, still warmer than its surroundings. But check out the footprints in the snow. 4 hours earlier, I walked through the snow and left footprints. You hear about the subnivean zone, a zone in the snow where animals burrow, and you hear that they can stay warm in that snow. So what you're seeing with those warm footprints is that the snow is an insulator, trapping the heat from the warm earth beneath it. And when I stepped in it, I'm releasing it. Over here, you're seeing that the rocks are still cooling, but a little bit warmer than their surroundings. All right, it's 7:30, 9 hours since we started, and it's more of the same with the big guy. But hey, check out the small ones. They're looking pretty much the same temperature as their surroundings. You see a little heat coming from the underside of the larger pudding stone, but they're getting real similar to their surroundings. Hey, that pudding stone is getting harder to see. That's because its temperature on the surface is getting close to that of the snow around it, but the pits are still warm. How about my small ones? Those guys are almost invisible now. And they're almost invisible because there's no temperature difference between the snow and the rocks themselves. They have completely reached the same temperature as their surroundings. And let's see, it's 9:30 at night, so yeah, just a short 11 hours since we put them out. Oh my God, my pudding stone's been stolen. No, it hasn't, but it has reached the same temperature as its surroundings now. It's 11:30 at night, 13 hours after we began, and you can see that except for a few pits that are just barely warmer than the surroundings, it has reached the same temperature as the outside. If you're under the impression that 21st century geologists were the first ones to discover that rocks could store and transfer heat, you're sadly mistaken. And on that note, I'm going to obnoxiously tell you to tune in next week for part 2 of this series. We're going to have a look at Native American soup stones. We're going to have a look at this ancient site and identify some of those artifacts ourselves and learn how to identify them. We're going to experiment with soup stones ourselves, not artifacts, but stones I had just found. And we're going to discover whether or not we can use thermal imagery to identify desirable stones on a beach. Join me.